Hello everyone and welcome back. Today was the last day of the lectures and it was a very interesting day. So I would like to give a retrospect of what I did. So this will be the second part of the DESY and Witten video series, let's say. So this series is a bit like a diary of what I did actually in Hamburg in this week. And like there's a good German saying that is called that everything has a single end unless it is a sausage. Because sausage has a two ends and Germans like to eat lots of sausages. It's a tradition here, so it's a saying in Germany. So everything needs to come to an end, and this also has come to an end. And it was an incredible lecture series by Witten. Like it says, it was a complete masterclass. I learned a lot. Especially today, Witten focused on different definitions of entropy, which you might know that I am very obsessed with entropy from my previous videos. And I learned a lot of things about it, and I interacted with him today a lot. I asked him like 4 or 5 questions in the class, and besides that, we talked. And after the lecture, he signed my lecture notes, and we talked about my development in physics. I mentioned him that I'm an undergraduate student and he was impressed and stuff. And I asked him to interview him actually for a few minutes and he agreed. But unfortunately, due to the hectic situation around the students, and also he I think had to leave, so we couldn't unfortunately make it happen, but he actually agreed to do it. But maybe in the future, because I'm sure that our paths will cross again in the future. I mean, he's the best physicist in the world. So if I want to become, if I will be at least the 50% of the physicist that I claim to be, then I'm sure that our paths will cross again. And first of all, what I want to focus here is our discussions in physics. And what were the lectures about today? So today, as I told you, we focused on entropy and different kinds of entropy. The initial lecture, I believe that he gave an overview of definitions of entropy, like Shannon's entropy and how von Neumann developed its quantum version and how it is distinct to quantum mechanics and stuff. And today in the lecture, what he did was to define, for example, for a star, how would those different entropies interact? So in a way, he generalized Bekenstein's work on black hole thermodynamics that revolutionized the field back in 1970s, I believe, which paved the way for famous Stephen Hawking to publish his most important work that is on Hawking radiation. So, I was unaware of all of this field. In 2006, he mentioned a guy who completely revolutionized this kind of mathematical proofs that is related to this field, where he gave a definition for black hole entropy using solely on von Neumann entropy, which is the entropy that is defined on quantum level. So again, Witten, it was a fascinating thing to me because, for example, he took a star and he defined on that star 2 distinct entropies and he summed them up. And my initial concern was like, how can you do that? Because, yesterday I also asked him, and today in the lecture I asked him, how can we define, for example, because, how can we have a different distinct definitions for a single phenomenon? We have a concept called entropy, which we claim it to be the most fundamental thermodynamic principle, that even the flow of time depends on this structure, and you claim that it has 2 distinct entities. So it has both a macro and a quantum level, and you just sum them up, and this doesn't make sense to me. And I asked this question to him, and he basically said that, no, we have 2 different distinct definitions of entropy, and I never knew about this. For example, he said in quantum level, you have, as I told you, a von Neumann entropy. And since every evolution in quantum mechanics is unitary, then your evolution matrix, I mean, the entropy stays the same. It's crazy, you know. So in a way, if you just look at von Neumann entropy, the entropy doesn't increase. It stays the same. What increases is the thermodynamic entropy, and the actual entropy of your total system is the summation of these two distinct entropies. So this seemed crazy to me, because I thought that thermodynamic entropy in some way should be linked to von Neumann entropy. So because it should be like the asymptotic limit of, I mean, thermodynamic entropy should be the asymptotic limit of von Neumann entropy, since it's like the macro version of it. But Witten said this isn't the case. No, they are two different entities, and the second law of thermodynamics and the increase of entropy, that is always the case for a given closed system, is only true, he claimed, for a thermodynamic entity, so entity of the entropy. So it was a complete shock to me. I mean, I didn't know anything about it, and I think this is wrong. I mean, I think, and he also claims it, that we need a better intuition about how gravity and entropy insights can be united. That's where we are lacking right now, he said. We need new insights, and I think the new insight is this. I think the new insight comes from giving a broader definition for entropy. Because, I mean, it's crazy. I mean, I don't get it. I mean, and I don't understand how he doesn't see any conflict in this at all. So this is where our ideas differ at first. But besides that, like, the mathematical masterclass given by him was incredible. I mean, you could see, I mean, I explained this in depth yesterday about how he can unite his physical intuition as with mathematics, and how he's very good at both. Well, he is really. But besides that, to be honest, I mean, his interactions generally with questions and with professors weren't that impressing to me. And like, he could have delved more in depth to some of the questions that were asked. I mean, not specifically by me. I mean, my questions were answered very actually in detail, also besides the lectures. But I mean, I think his attitude could be more productive, let's say, without hurting anyone's feelings. But besides that, like, he's doing this out of like charity. I mean, he doesn't care about. I mean, he's even a professor in Hamburg, so it's like a privilege for all of us, also people in Germany, in Hamburg, in Europe, to be here. And actually, one of my friends, we just met, I think, just by coincidence. He was my friend from Utrecht summer school, and he's from Portugal, and we just met here again. So it's like everyone in Europe who is interested in this stuff have come here to see Witten. But besides that, like, of course, like, he mentioned lots of things that were out of my grasp, because he was going too fast, because like there is like 120 pages of lecture notes that he had to finish. Actually, I had it by myself, but he got it signed, and I just wanted to make it a special bind in Germany for those lecture notes. So I gave it to a bookbinder near my place. But I mean, I will get it tomorrow morning, so I can't show you right now, unfortunately. So in a way, he had to be very fast and give us the taste of what a black hole thermodynamics can offer. Also, we talked about, for example, how wormholes are created, and like how a quantum structure resembles a wormhole structure. So I think there's a famous correspondence. I think, let's say it is like a, in mathematics, it's like a conjecture. I think the word is conjecture. That conjecture assumes that general relativity's wormholes are equivalent to entanglement, which corresponds an effect in quantum mechanics. And I think this was founded by Leonard Susskind back in 2018. It's something quite new, and they actually tried this in a laboratory. Actually, I think I talked this with Professor Mustafa Ali Soy, who is, he's like my mentor. I really, he's an incredible physicist. So I think we discussed with him back in 2020 after Saskans in using a supercomputer or a quantum computer. I don't really remember exactly the details. I think there was some even a Greek woman at the head of this project, and they claimed that they actually found this kind of equivalence between quantum effects and wormholes. But unfortunately, I think it was then disregarded, like it was disqualified because of some fundamental mistake they have made in the computer itself. So they couldn't prove it, let's say, using a supercomputer or a quantum computer. But I think at the end of the lecture, that was what Edward Witten was mentioning. But of course, I couldn't quite follow it, and I just arrived from the lecture, so I can't really give you the details because I haven't studied in detail again. So, but in a way, he showed that entanglement and wormholes are causally related. And I asked him a question on this point. I asked him that in lecture, I asked him whether we can, using any quantum effects, can send information through this wormhole, and the answer he gave was that basically you can't, because you see, he said, wormholes corresponds to entanglement, and since we cannot send information faster than light using entanglement in quantum mechanics, we cannot do the same in a wormhole as well. So this is the answer he gave me, and it's quite sound. But at the lecture, I cheated a bit. I looked at the web and if this structure existed, and I've seen that there are some recent papers that claim that there are some decoherence and other quantum phenomena that can occur in this kind of structure that is formed at the zeroth boundary of the two causally connected black holes, which is a wormhole in that case. I think it is called Hartle structure, but I'm not sure again because I'm not an expert on this and I just looked at that lecture while asking to Witten. So in these were generally what I got impressed in those lectures. And again, the way he looked at entropy and made calculations again. Also, he defined different entropy that I haven't seen it before. I think it's called Reiner entropy, and it is related to von Neumann entropy. And how it is related is that there's like an alpha term, 1 over alpha minus 1 or something, then it is multiplied with a traditional entropy term, and when you take alpha goes to 1, it goes and collapses to von Neumann entropy. So it's an incredible new definition, and it generalizes, I think, entropy, von Neumann entropy, from a special case to a general case. So I'm not exactly sure how it is useful, and Witten didn't delve into the mathematical structure and how it is defined historically, this kind of entropy. But it was a fascinating thing to observe, because yesterday, again, I talked with Witten and he told me that von Neumann entropy is the most central, and today we arrive to the lecture and we say that, no, we have two different distinct entropies. By the way, sometimes instead of von Neumann entropy, we use Reiner entropy. So it's crazy to me, like, again, it's completely different phenomena. I mean, than what I am used to, and also another interesting thing is that we define something called mutual entropy, and in the lectures we prove that it is always bigger than zero. So it's also an incredible thing to think about. So yeah, these were generally what I got impressed in those lectures, and Witten was an incredible. I don't want to say lecturer because it would be wrong. He's a very good physicist. He's an extraordinary mathematician and thinker. His insights are so in depth. Again, he never speculated today. He said, "This is I know. This is no. Okay, this is it." This was his general approach, and to be honest, this is not my style. He has completely different style than me in everything he does. Maybe our styles match, since I'm also a very mathematical thinker and naturally, but the way he teaches and the way he creates his ideas are completely different than mine. I think that his strong suits are definitely in understanding the concepts in depth, not to speculate on new topics. He just leaves those stuff to other people. For example, you can look at history to understand this better. In 1997, holographic principle was developed by Yuval Maldacena, who is now his colleague at IAS, Institute of Advanced Study at Princeton, who Edward Witten is. I mean, Edward Witten is a professor there right now. So Yul Maldacena developed holographic principle, but it was Witten's paper that put what holographic principle into the map. So like Witten waits someone to develop something, an idea, he says, oh, this is nice, and he understands that idea better than that person that wrote it. So this is the Witten's power, I think, in general. So it's incredible to see how a mind like that functions. But again, like every great scientist, I mean, there are some things you agree, there are some things you don't agree with his style and with his ideas. And like it was a very pity that we couldn't make a video together for even a few minutes. I was gonna ask him about his mathematical development, which is unknown actually. I mean, because there's a lot of ambiguity of how he moved from his undergraduate degree, which was in literature, a Bachelor of Arts degree, to a PhD in physics at Princeton. So it's crazy how that like movement happened. Well, of course, it is known that his father, Louis Witten, taught him physics from earlier ages. But I mean, how can you learn a lot from a single father? I mean, yes, your father can influence you a lot, but I mean, you cannot learn the entirety of physics and mathematics on your own. So somehow he should have learned, he probably learned mathematics, for example, by following a certain curricula or books by himself. That was what I was going to ask him today, but unfortunately it didn't happen. But as I told you, I very highly doubt that this was the last time that we meet, because I think our paths will cross for a long time. So thank you for your interest in this journey, and have a nice day and stay with physics. Bye.